Hello, my name is Michelle Chong, and I'll be speaking on the ellipsoidal bounds of the reachable set for a class of time-delayed nonlinear systems with bounded input. This is a presentation recorded for the 2022 European Control Conference. The reachable set of a dynamical system with inputs contains all the solutions of the dynamical system for all initial conditions and inputs of interest. More specifically, for a dynamical system depicted here, the forward reachable set is the set of all solutions to 1 for initial conditions and inputs that reside in given compact sets X0 and W. Reachable sets have many uses, such as in state and parameter estimation and in set-based estimation, in the references denoted here. It's also used for robustness analysis, controller design, security and safety verification, and many more. Except for very simple cases, such as linear time invariant systems, the computation of the reachable set is typically difficult without resorting to conducting simulations for all possible initial conditions and inputs. Since it is impractical to do such extensive simulations for complex systems, instead, we'll perform approximations of reachable sets. For example, this plot right here depicts the reachable set of a dynamical system with initial conditions starting from the origin, and for all inputs within a compact set. We could perform over approximations of the reachable set to ensure that we have no false negatives. That is to say that the states belonging to the true reachable set, but not to its approximation, which is the one shaded in orange. This can be done with many different geometrical shapes, such as a polytope, a hyperrectangle, or ellipsoids. The choice of the bounding shapes influences the computation time. Typically, the tighter the bounds, the harder it is to compute. In this work, we focus on ellipsoidal bounds, as ellipsoids can be written in this particular quadratic form with a positive definite matrix P centered at the central point C. This lends itself nicely to Lyapunov-based methods, which employ quadratic Lyapunov functions, which allows us to deal with a class of time delay nonlinear systems. Given a time delay nonlinear system, existing work that uses ellipsoidal approximations have been done for time delay linear time invariant systems with increasingly tighter bounds over the years, using more advanced methods. This has also been done for linear time varying systems, and to the best of our knowledge, there are no results for nonlinear time delay systems. The contribution of our work is a step in this direction by considering Lur'e type time delay systems. Specifically, the system has a linear and a nonlinear part, where the time delay appears in both the linear and the nonlinear terms. We assume that we have time-varying time delays, with bounds on the delay and its rate of change. We'll see that the bound on the rate of change is a consequence of the Lyapunov function or functional that we have chosen. We also assume that the nonlinearity is sector bounded, and we have bounded inputs. For simplicity, we have assumed that the system has been initialized at the origin, and we only have one time-varying time delay. Extensions to more time delays and initial conditions that do not originate from the origin can easily be done. Examples of real systems that belong to this class includes a gene regulatory network called a repressilator, which we've shown here. This particular model models the mRNA and protein concentration levels of a gene network. Another example can be found in neuroscience for a column of the cortex, which models the pyramidal neurons and excitatory and inhibitory interneurons. In fact, the plot of the reachable set shown a few slides ago comes from a cortical column model as we have depicted here. As alluded to a few slides ago, our objective is to bound the reachable set with ellipsoids, as they lend themselves well to Lyapunov-based methods. For simplicity, we have considered systems which start at the origin. Consequently, we can use ellipsoids that are centered at 0, which can be written as follows, with P being a positive definite matrix. Suppose that there exists a scalar function V that maps the state to a scalar, which is 0 at the origin. And also by considering bounded inputs, suppose that this particular function satisfies this inequality, then the function V is upper bounded by 1 for all time. Now, if V is lower bounded by X transpose PX for positive definite matrices P for all time, then we can conclude that the reachable set Rx is over-approximated by the ellipsoid E of P, as defined here. This is the approach that we'll take to construct our bounding ellipsoid. And our task is to now find such a function V. For time delay systems, there are two Lyapunov-based approaches, the Krasovskii and the Krasovskii-based methods. The Krasovskii approach uses a function and requires some solutions of the time delay system to satisfy an inequality, which results in a method that is independent of the rate of state change of the time delay. The downside is that employing the Krasovskii method requires a model transformation that is not suitable for Lur'e type systems, in the sense that it would transform the nonlinearity that no longer preserves the nice properties that we have originally. On the other hand, the Krasovskii method uses functionals that maps the set of continuous functions to a positive real line. This here denotes the set of all continuous functions from the interval minus h ends to 0 to the state space Rnx. By using a Lyapunov-Krasovskii functional, we do not require a model transformation, which works well for systems with nonlinearities. The downside is it depends on the rate of change of the time delay. Since we consider a Lur'e type time delay system, we have chosen to use the Lyapunov-Krasovskii functional. We have chosen to construct a Lyapunov-Krasovskii functional as follows, where we have the first term, W0 term, to deal with the parts with no time delay, and hence only dependent on X, and two other terms, W1 and W2, which depends on the states with time delay. And they are constructed as follows. Important in terms to point out are the symmetric and positive definite matrix P, which we're going to use to build our bounding ellipsoid. Other terms are Wm, which is the bound on the input, which we assume that we know, and the other matrices, S, R, X, Y, Z, W, which have the properties stated on this slide and can also be found in detail in the paper. We can show that with this particular choice of the Lyapunov-Krasovskii functional, we can obtain the inequality that we needed from before to show that the ellipsoid does indeed over-approximate the reachable set. Details of this derivation can be found in our paper. As mentioned earlier, the symmetric and positive definite matrix P, which have been obtained from our linear matrix inequality condition earlier, provides us with an ellipsoid that over-approximates the reachable set Rx. A natural question to ask is then, can we tighten this approximation? To do so, we minimize the volume of the ellipsoid subject to the derived LMI conditions from the previous page. Since the volume of the ellipsoid is proportional to the inverse determinant of P, minimizing the log of the determinant of the inverse of P minimizes the volume of the ellipsoid. This can be further formulated as an LMI to be solved in conjunction with the previous set of LMI conditions, such that we get a minimized ellipsoid, a tighter ellipsoidal bound. Details on this can be found in our paper. We can now apply our results to a particular example. We'll use the cortical column model that we spoke about a few slides ago. This particular cortical column model has two neuronal populations whose electrical activity is captured by the state X1 and the state X2. This model has a time delay that varies between 0 and 0.1 with a rate of change of 0.25. And the input to this model is a uniformly distributed signal between 0 and 0.1, which is bounded by 0.1. By solving the conditions we derived earlier, we obtain the outer ellipsoid in red without minimizing the volume of the ellipsoid. But actually, before going into that, I like to point out that the solid blue line is the reachable set. And on the right, we've plotted the solution to the model for a very particular choice of a bounded input. So going back to computing our ellipsoidal bounds, by solving the conditions we derived earlier without minimizing the volume of the ellipsoid, we obtain the red ellipsoid depicted here. And by minimizing the volume, we obtain a tighter bound on the reachable set. To conclude, we have over-approximated the reachable set of a Lur'e type time delay system with bounded inputs using ellipsoids, which we have obtained using Lyapunov-Krasovskii functionals. This boils down to linear matrix inequality conditions, which are computationally efficient if they are feasible. By gaining the computational efficiency of ellipsoidal bounds, we have sacrificed the accuracy of the approximation, as we have seen in example on this slide. Further work will include considering modeling uncertainties and the applications of these results to safety and security verification. I thank you for your attention. I'll be most happy to hear from you if you have any questions or comments. Thank you.